Okay, hi guys. So in this lecture, we'll be discussing on the rate of disappearance and rate of appearance. So let's get started. Rate of disappearance and rate of appearance. So rate of disappearance is defined for reactants, and rate of appearance is defined for products. Okay, so we have an example like A gaseous plus 2 moles of B gaseous forming 3 moles of C gaseous is a reaction. So we'll be defining rate of disappearance for A and B, and we'll be defining rate of appearance for C. Okay, so let's now define what is average rate of disappearance and appearance. So average rate of disappearance or rate of appearance, we can write it like something. So first of all, it is defined by macroscopic time interval, defined by macroscopic time interval. Then we have, let's say we are saying average rate of disappearance of A over a macroscopic time interval would be nothing but minus of delta A by delta T. It can also be written as minus of concentration of final concentration of A minus initial concentration of A divided by time taken to reach the final concentration from initial concentration. Okay, and average rate of appearance of A, rather the disappearance of B, can be written as again minus delta of change in concentration of B divided by change in concentration of, rather per unit time, change in time. Then this can be written as concentration of B final minus concentration of B initial divided by TF minus TI. Okay, so this actually represents the molar concentration. Okay, then let us define the average rate of appearance of C. This can be written as change in concentration or molar concentration of C per unit change of time. So this can be written as again change in molar concentration of C, CF minus CI divided by TF minus TI. Okay, and if we look at the graphs of the same, we would be having graph something like this. On the x-axis we have time, and on the y-axis we have concentration. So let's say we are talking about concentration of A. So with respect to time, it is decreasing. Okay, and we have been given that, let's say at we are taking time in minutes. Okay, so let's say at from 0 to 10 the concentration of A was 0.8, and at time t equals to 20 we have concentration of A as 0.4. So from this we can write that rate of disappearance of A can be written as minus concentration of, rather we have to find the rate of disappearance of A between time t equals to 20 and between time t equals to 10. So TF would be 10, TI minus 10 minus TI would be 10, rather TF minus 20, TF would be 20 and TI would be 10. And what would be AF? AF would be nothing but 0.4 and AI would be 0.8. So rate of disappearance of A would be minus of minus 0.4 divided by 10. So this is nothing but 0.04 moles per minute. Okay, or rather not moles, molarity per minute. Suppose we have a graph something like this of the concentration of C with respect to time. Again, time minutes is in minutes. So let's say we have something like this graph. So at t equals to 10, we have a concentration of C as 0.2, and at t equals to 20, we have concentration of C as 0.8. So rate of appearance of C can be written as Cf minus Ci upon Tf minus Ti. This is Ti. So we can write that Cf was 0.8 and Ci was 0.2 and Tf was 20 and Ti was 10. So it would be 0.06 m per minute. Okay. Next, let us define the instantaneous rate of disappearance or rate of appearance. Okay, so this is defined by microscopic time interval. Okay, and instantaneous rate of disappearance of A would be written as minus dA by dt. Okay, and instantaneous rate of disappearance of B can be written as similarly minus dB by dt. And instantaneous rate of disappearance of C, rather rate of appearance, C is a product, so it would be instantaneous rate of appearance of C can be written as dC by dt. Okay, so we can also write that the instantaneous rate of either disappearance or rate of appearance can be written as limit t tends to 0, rather delta t tends to 0, and minus or plus del of concentration of x divided by del t can be written as minus plus d of c by cx by dt. Okay, and graphically we can say that if we have a graph of concentration of any reactant or product with time, let's say the graph was something like this, then at any particular instance we are taking the slope of this graph to represent instantaneous rate of disappearance of this reactant. Okay, so this would be a negative slope. Okay, so with this we come to the end of this lecture. In the next lecture we'll be continuing on seeing more on rate of reaction and rate of disappearance and rate of appearance of reactants or products. So till then, good luck and goodbye.